So good morning to this little bit of a revision lecture in state space, and what we've got is two parts to this problem. First of all, we have the open loop system here, which we're going to convert into state space. Then I'm going to add in a control system here from which we're going to compute our control law, and then we're going to get the closed loop state space equations. So let's have a look at this. So we've got a little transfer function here, 4 over s plus 4, 2s plus 3, s squared plus 4s plus 9, non-minimum phase transfer function here, which has got the same number of poles and zeros, a little first order sensor there and a little first order sensor there. I've labelled the input u, the output y, called this state x1, and then because it's a second order system we'll have two states associated with this box, x2 and x3, we'll have a state associated with this box x4, that one x5 and that one x6. So we're expecting a 6 by 6 state space equation, and this will be the open loop state space equations. Now the first thing we've got to do is, because this function here has got the same number of poles and zeros, we need to re-badge this one as a slightly different block diagram. So if we think of the block diagram, minus 2s plus 1 over s, we could write that as minus 2 plus 1 over s. And so we could reposition this block diagram as something slightly different. So we could have the minus 2 block there with the 1 over s, and we could have this as the alternative block diagram. So that's giving us the minus 2 plus s, minus 2 plus s. So that'll make life a little bit easier for us when we come to do the state space equations. And we can label this variable then x4. So, having done that then, we can proceed now to obtain the state space equation. So we work through each box one at a time, get the equations, collect them up into one big state space. So what I'm going to do is I'm going to put the 6 by 6 state space equation here and fill it in as we go. So we're going to have x1 dot, x2 dot, x3 dot, x4 dot, x5 dot, x6 dot. There's the derivatives of the states there. That's going to equal to a matrix here now. It's going to be a 6, that's 1, 2, 3, 4, 5, 6. Let's break it down into blocks. So there's our 6 by 6 matrix, and this is going to be x1, x2, x3, x4, x5, x6, plus u. So there's our state space representation of the open loop system, and what we're going to do now is fill in boxes. So let's look at the first one. We've got this is this times this, so we've got x1 equals 4 over s plus 4 times u. So we can move this term up here, so we get s plus 4 times x1 equals 4u. But s times x1 is x1 dot, so you get x1 dot, take that over, minus 4 x1 plus 4u. So here's our first sort of equation, x1 dot is minus 4x1 plus 4u. So that's going to go a 4 in there and a 4 in there. So that's our first one done. So now go on to the next one, which is this one here. So this is a second order system, so we're going to do this one in companion form. So what we have is we've got x1 feeding in, and we've got a block diagram here, which is 2s plus 3 over s squared plus 4s plus 9, and we don't quite know what the output is at the moment. So second order system, companion form, so it's going to be, and it's going to be the second and third states. It's going to be x2 dot, x3 dot, it's equal to a matrix here times x2 and x3 plus another matrix times x1, because x1 is the input this time. So companion form is going to be 0, 1 minus 9 minus 4, and that's going to be 0, 1. Remember, in companion form, these numbers here and those numbers there in reverse order with negative signs, there's always a 0 and a 1 there. The output from the system, so we call it y bar, or y hat even, will be given by times x2, x3, and this will be given by these numbers in reverse, so it's going to be 3, 2. This time it's with positive signs. So the output from this is actually 3x2 plus 2x3. It's actually up to 3x2 plus 2x3. So that's the actual output there. And that's come from this little equation here. So now we can put this into our state space. So x2, so now that 0, 1 minus 9 minus 4, and 0, 1 on x1. So x1 is the first row, so that's going to be 0, 1. Because this has to feed in on the x1 column. If you look at x3 dot, it's minus 9, x2, 4x3 plus x1, so x3 minus 9, x3, 1x1, and minus 4x3. So there's that one done. That was quite straightforward. You can have this. This could be second order or third order, could be any size. So let's move on to the next one now, which is this part here. So now what we've got is, we've got a little block diagram with the minus 2 in there, and we've got a 1 over s in there. This variable is x4. This is on a plus and a plus. That's the output y, and this signal here now is this one here. It's 3x2 plus 2x3. So we can say now we can get an expression for x4. So you've got x4 is this times this. So x4 equals 1 over s into 3x2 plus 2x3. If we move the s up here, it simply becomes x4 dot. So that gives us our next line now. X4 dot is 2x2, so that's going to be a 2 in there because that's picking up the x2. And, sorry, 3x2, not 2. And 2x3. So we're going to pick a 2 there. So that's our state space equation. That we can also get what the output is y. So y is going to be minus 2 times this plus x4. So you can see that y is minus 2, so that's minus 7, minus 6x2 minus 4x3 plus x4. So that's an expression for y. Y is going to be minus 2 times that plus x4. So we need to put that on the diagram, so it's minus 6x2 minus 4x3 plus x4. So that's the output from our system. So we've got 2 more to do, and then we'll have got our open loop state space equations. So let's look at this one now. Into this box here we've got a 10 over s plus 10, and output is x5, and the input is 3x2 plus 2x3. 3x2 plus 2x3. So we can now say that this is this times this, so you get x5 equals 10 over s plus 10 into 3x2 plus 2x3. So move this up here, so we get that s plus 10 times x5 is 30x2 plus 20x3. S times x5, x5 dot, so you get x5 dot. 10x5, and the other side will be minus 10x5, so it'll be 30x2 plus 20x3 minus 10x5. So x5 dot now goes in the next line. So it's going to be 30 x2s, so I'll put 30 in there, because that's the x2 column. 20 x3s, so that's 20 x3s, that's the x3 column. And minus 10 x5, so that's x1, x2, x3, x4, x5. It's minus 10 x5s, and it's got nothing else going into it. So we're now on to the last one. Which is going to be this one here. So got your box again. 20 this time. Over s plus 20. The output is x6. And the input this time is y, which is minus 6x2 minus 4x3 plus x4. So we can now say that this is this times this to give us that x6 is 20 over s plus 20 into minus 6 x2 minus 4 x3 plus x4. Move this up here, so you get s plus 20 times x6, multiply it out, so it's going to be minus 120 x2 for minus 80 x3 plus 20 x4. So again, some quite big numbers in here now, but it doesn't really matter. S times x6 is x6 dot, so x6 dot is going to be minus 120 x2 minus 80 x3 plus 20 x4 minus 20 x6. That's plus 20 on this side, minus 20 on that side. So that gives us our last equation now. So minus 120 is not going to fit in here. 120 in there. Minus 80 in here. Then we've got 20 x4s. That's going to be 20 in there. And minus 20 x6. So this now represents the open loop state space equations for the system. What we can do next is to work out some closed loop state space equations, and we're going to do that by adding in now a controller. So I'm going to add in two parts of a controller, a PI controller and a phase lead controller. So in here we're going to have a PI controller, and that's going to be fed back off x5. And then we're going to have a phase lead controller in here. And that one's going to be fed off x6. And we're going to have some input here, V. So the next thing we're going to do now is we're going to add in, this has now got an extra two states in it, two states one from the PI controller, one from the phase lead. We're going to extend the state space out to a 8 by 8 and work out the closed loop state space equations. That'll be in the next following video. Right, so we're now on the second part of the state space example, where we're now going to use the control law to get the closed loop state space equations. So the first thing I've done is, because we've got an extra state here and an extra state here, because we've got two S terms, I've extended the states by 2. So I've gone from x6 to x8. So I've now got an 8 by 8 matrix here, and a 8 by 1 for the input u. And the first thing we're going to do now is to, again, because these are the same number of poles and zeros, these are not ideally suited to a state space representation. So we're going to just convert these into two subblocks. So this one's quite simple to do. If we've got 6s plus 2 over s, we can know that as 6 plus 2 over s. So we can rewrite this box as a 6 and a plus 2 of rest. So that one's going to be quite straightforward. So that's going to be a bit smaller. So that's giving us a 6 and a 2 of rest. So we've rewritten the 6 s plus 2 of s as 6 plus 2 of rest, then put it in as that block diagram, and that should be a plus, shouldn't it, to be correct. And next one's a little bit more tricky. The 3s plus 3 over s plus 10, we have to write as a plus b over s plus 10. So we split into a constant plus a fraction. So if we multiply everything by s plus 10, we get 3s plus 3 equals a into s plus 10 plus b. Now we can now do a compare coefficients. So coefficient of s is 3 and here is a, so a is 3. So that gives us the 3. Then this number is 3. 3 tens are 30, so 3 has got to be 30 minus 27. So we could rewrite this as 3 minus 27 over s plus 10. So I'm going to take this box out here. I'm going to rewrite this as 3 and a 27 over s plus 10. And this time we'll put a plus and minus in here to give us the minus 27. And then when we've done that, we can call, say, this state here x7 and that state there x8. So x7 and x8 now are our additional states that we've got from our controller there. So we're now in a position to work out the control law and then get the closed loop state space equations. So we've got input signal here v, y is given by this term over here. So we could work out v minus y as 6 minus 6x2 plus 4x3 minus x4. So that's that signal there. And then we can start to work out the signal there, there and there. So if we get the different parts now, let's see how we do this. If we've got the signal here, for instance, it's going to be 3 times this minus x8. So it's going to be 3 times this. So we've got 3v plus 18x2 plus 12x3 minus 3x4 minus x8. So that term there is going down there. We've got an x5 here, so this term has got a, and that's going to be a plus and minus there. Put the minus in properly. So we've got minus x5, so that signal there now is going to be the same as this one, but it's got a minus x5 in. So this signal here has got a minus x5 in. And then that whole thing then gets multiplied by 6 and added in by an x7. So it gets 6 times this now. So that's going to be quite easy. So 6 times that would be 6 3s is 18v. 6 18s, 6 8 is 48, 104 plus 104 x2. Then we've got 6 12s, 72 x3 minus 6 3s are 18, 18 x4 minus 6 x8 minus 6 x5 plus x7. So this signal here now is what's going down there. So this is actually our control law, mu equals. So there's our control law now, and what we're going to do now is to put the control law U into here. So we've got a 4U here. Notice we've got a 4 there. So a good idea now to be multiplied, work out what 4U is. So we get 4U, can start here maybe, 4U. We're doing 4U because we need 4U over here. So 4 18s are 72. 4 of these will be 416. 4 72s will be 288. 4 18s will be 72. 4 6s are 24. 4 6s are 24. And 4 times 7 will be plus 4x7. So this is 4U now, which is our, and this is our control law, because we worked out what that signal there is. So we now put these numbers now into the control law, but before we do that, we'd also be wise to get a little state space equation for this one and for this one and put those two equations in here. So I've missed out on that a little bit, but we can do that quite quickly. So let's just rub this bit here out. I'll keep our control law, having derived it. So let's look at this one here now. X8, we've got a little box, quite a complicated input. We've got V minus 6x2 plus 4x3 minus x4 going into the box. And out of the box we've got x8, and this is 27 over s plus 10. So now we've got this is this times this, so get the x8 will be, or x8 multiplied by, so x8 is equal to 27 over s plus 10 into v minus 6 x2 plus 4 x3 minus x4. And we can move the s plus 10 up here, so we'll get s plus 10 times that, and then we get s times x8 is x8 dot, so we'll get x8 dot 27b. Then we've got 6 27s, so 6 times 42, 12, 14, so 144, so that'll be minus 144 x2. Then we've got 4 27s, so 4 times 27, 28, 808, so that's going to be plus, so it's a sign wrong there, isn't it? That should have been a plus there, that should have been a plus there, sorry. And there's a plus there, so that's a plus there, so that should have been a plus. Spotted that one. Plus, let's go back to 427 to 108, 108 x3 and minus 27 x4. And then we can bring over 10 x8 as well, so this will be minus 10 x8. So here's our x8 equation now. It's got a v term in, but it's got 144 x2. So it goes on the bottom line, x8, so 144. So you've got 144 in there, 108 x3, 108 in there, minus 27 x4. So it can be a minus 27 there, 10 minus 10 x8, so it'd be minus 10 in there. And we've also got a 27b, so I have to add in now an extra slot in here. One, two, three, four, five, six, seven, 8. There's our 8 boxes, and we want a 27 here, so it's going to be a 27 down there. That's the 27 multiplied by v. So there's our state space equation for x8. And then we need to do the last one, which is x7. So x7 is this from here. So we've got a little box, 2 over s, x7 coming out. And into it now, we've got this term here. So this term is a little bit more complicated. So I have to go back to this one. It's going to be this part here, which is going to be x8. Let's try as x8. So it's got an x8 coming that way. It's got a minus x5. And it's got this signal here, which is, well, it's got the x8, it's 3 times this. So it's going to be 3 plus 3v plus 18x2 plus 12x3 minus 3x4. So this is a bit more complicated, this one, but because it's a 2 over s term there, it isn't too bad. So we'll get this is this times this, so we'll get that x7 equals 2 over s multiplied by these terms here. So that would be 3v plus 18x2 plus 12x3 minus x5 plus x8. Move this s term up here, so that will become x7 dot. And then we can multiply everything by 2. So 2 3s are 6, so that will become a 6. 2 18s, 36. 2 12s, 24. 2 will just go in there. And a 2 will go in there. So here's our last equation, x7 dot equals 6v. So x7 dot will be 6v. It's going on the 7th line here. 36x2, so I have a 36 in here. A 24x3, so I'll go in there, and minus 2x5. 1, 2, 3, 4, 5. Minus 2 in there, and 2x8. So we've got a 2 in there. It's got a 2 over s there, so it looks correct. So there's our full state space closed loop system. Other than now, we've got to put 4u now. 4u is going to feed in here, and that's going to feed in on this line here. So we're going to do that in a different colour, just to highlight the change. So let's have a look at this now. So 4u is equal to 72v, so I'm going to put a 72 in here. That's the first one gone. Then we've got a 416x2, so we've got 416 in there, and that one's gone. We've got 288x3, so that one's gone. We've got minus 72x4, so that one's gone. Got minus 24, or minus 24x5, so that one's gone. Got 4x7, 4x7s, and we've got minus 24x8s. Now, because we've done that, we've actually replaced now the u, the 4u. So the 4u has disappeared, so that means this part here has disappeared. And these now represent the closed loop state space equations. So the general technique is obtain your open loop state space equations. Then, if you've got some controllers here, simplify these into rational forms, add those in as extra states into your closed loop state space equations, then derive the state space equations for these individual bits, add those in. Then when you've got those, start over on this side, follow the control signals round and work out what an equation for the control law here by working out this part, then that part, then this part, then that part, then this part and that part, adding them together and eventually get an equation for u. That'll give you your control law. And then watch out for, and there's a 4u there, so work out what that number is. Basically it was 4u. Then that gives you your complete control law. And then these numbers then feed in on the particular line on your u. And that will give you your complete closed loop state space equations. I'm back again on this thing. I just double checked my answers and those small numerical errors. That one should have been 432, that one should be -6, and that should have been 162. No one here to tell me my small mistakes, but I hope now it's the correct answer. Good luck.